Okay, maybe let's get started. So welcome to the third part of our series. So far we have talked about why galaxy surveys are important, what kind of science you can do and what kind of precision it can get. Then we also talked about various details of what kind of information galaxy surveys can provide. And if you are going to look at any available data set, you'll have understanding of, okay, what kind of different photometric band, redshift, spectra, position on the sky, all that kind of information will be available. So probably that will help you understand these kind of catalogs. So today we also talked a little bit about Fisher matrix, how to use that to figure out what kind of precision you're going to obtain if you're going to do future analysis, where you're going to sort of think about how to optimize whatever you're going to observe. So today I'm going to talk about a bit more towards physics, and there are some very standard probes which can be measured and analyzed through these galaxy survey. Two of them is Baryon Acoustic Oscillation and Redshift Space Distortion. So I'll try to tell you a little bit about how the physics of this works, what kind of things we look at when we want to do analysis of these things, and what kind of ideas or survey might give you optimum results if you're looking at something like Baryon Acoustic Oscillation or Redshift Space Distortion. All right. So we'll begin with something very basic, which probably all of you already know and you have heard, but I just wanted to bring this in the context of what we are going to talk about, starting from the early universe. And a lot of these things are covered in Paula's lecture in great detail. And whatever, some of this will be covered in Rishi's lecture when he talked about CMB. So I've already showed you this picture, our view of observable universe, starting from CMB, dark ages, and then various galaxy survey. And in all these different areas, we are trying to do better and better, improved measurement, right? Also, I guess you have seen this kind of diagram where we talked about scale factor a little bit yesterday as well. So if you think about universe and write it in terms of scale factor, where scale factor of 1 is today, and think about different kind of component, energy density of different kind of component in the universe, then they are going to scale differently. So for example, if you think about matter, it's going to scale by a cube because the equation of state W of matter is 0. So essentially it scales with volume, whereas radiation will have a to the minus 4 because radiation also gets redshifted on top of the volume, growth with the volume, a to the minus 4. And dark energy, which we don't know what exactly it is, and we're still trying to figure out, but in the scenario when it's cosmological constant, so it's a to the 0 basically, the energy density of this component doesn't change, but that's still one of the big question, in fact, we're trying to address. And if you look at, based on our current measurement, how these things are going to be in terms of the initial condition and just propagate that, you're going to find that there's going to be a radiation matter equality era, where the radiation, which was initially in terms of the highest density component of the universe, is going to be equal to the matter, and then it's going to subdominate because it goes at a to the minus 4 after some time. And there's some interesting physics happens at this era related to CMB, which we'll look at in much more detail. Also, there's going to be, so I guess you have heard this many times, the dark energy only recently dominated the universe, right? So what does that mean? So that is something you can see in this diagram. The matter has been dominant component for much of scale, if you look at in logarithmic scale factor of the universe, but it's only recently, roughly here, where matter and dark energy density were roughly equal, and now dark energy is dominating. So this is roughly redshift 1, where this is going to happen. And this is the regime where we are trying to constrain dark energy equation of state, if you are interested in. But if you can have measurement in this era, then you can constrain matter density very well. Okay. So going forward, you have to start. So just today, Paul was talking about initial condition of the universe. So if you, for the purpose of this presentation, we can just start by basically initial assumption, which seems to be very good so far from all the data set, is that the initial matter power spectrum was essentially scale invariant in terms of the metric perturbation. So that essentially means that the perturbation in the potential was constant. It's independent of scale. So at all scales, you'll find same perturbation. There's no special scale. And if you translate that through the density potential relation, you're essentially going to find the power spectrum, which is written in terms of the how the density is correlated two-point function is directly proportional to k. So p is proportional to k. This was something proposed a long time ago in this paper by Zeldovich in 1972, and later on, when people worked out inflationary scenario, they found more or less the same result with a slight tilt. And so that's why there is a ns, which is different from 1. So ns is, it's not k to the 1 exactly, it's k to the 1, k to the ns, where ns is a slightly different number than 1. Okay, so now when you start with this kind of picture of initial power spectrum, which is more or less scale free, which means ns is close to 1, what's going to happen is that all the processing from the initial power spectrum to us is going to change its nature. And most of cosmology is really trying to, so a lot of it is about trying to figure out what is this itself, and a lot of it is looking at evolved version of this power spectrum and then trying to work out what are the initial condition as well as what are the evolution terms, what are the equation. So you need to sort of have some rough idea of how does this evolve as you go along, right? So how does the evolved power spectrum would look like? And so the first thing is, if you consider this the cold dark matter scenario, and in the cold dark matter scenario, if you have the initial power spectrum, which is k to the ns, then there's going to be different regime, different scales is going to transition to different part of the universe at different time, a different scale factor, because of the size, right? So there's always going to be horizon size, roughly a over h, and so as a particular mode k2 is super horizon, which means bigger than horizon size, it's going to grow linearly like this. Then in radiation dominated area is going to be frozen, and then in matter dominated area it will again increase. But a different mode will do the same thing but at different a. And so what's going to happen is that at these large k, which is small scales, they are going to be frozen. These scales are going to be frozen beyond this, and these scales are going to grow. And so because of this different phase when it enters, we are going to essentially see an upturn. And so this is what we call radiation matter inequality. This turnover hasn't been seen in galaxy survey so far. And it's one of the things we are still trying to measure. This turnover, we have many galaxy survey, but we haven't seen this turnover. In fact, I'll show you data where you'll not see this turnover. And so the reason for that is that the scales at which this happens require large volume, and at those large volume, you need to have sufficient volume to have noise which is small enough to see the turnover. And we are hoping that the ongoing surveys will show us turnover. This is one of the things we really want to see. But there are some very complicated systematic issues which might limit us to see turnover even in the ongoing survey. So we'll see how that, what happens to that. Now, if you also consider the baryon part of it, baryons and photon, as you know, in the initial universe were coupled, and so the coupled equation essentially produced this kind of oscillations or sound wave, and this sound wave is also imprinted on the power spectrum. And so it's not just a turnover, but it's turnover with a BO wiggle, so Baryon Acoustic Oscillation wiggle. And you can predict what is essentially the scaling of this turnover versus this part. All of that can be predicted in a given model. And you can also predict what will be the amplitude and the locations of this BEO in a given model. So another way so that was a sort of Fourier picture, and Fourier picture is easiest to work on whenever you're doing sort of theoretical calculation. because things are simpler, different modes are decoupled, but you can also think about in terms of the physical picture, right, in configuration space, what's going to happen. So if you imagine like there is one location, which is the initial, okay, I can't pause this, so just the way this starts is everything is here at the same time. So that's the initial perturbation in the initial density field, where everything, dark matter, baryon, gas, neutrino, all of that is the same place. And then what happens is that with the as the time evolve, everything propagate forward. But because of things like neutrinos and photons, they are essentially highly energetic. They expand faster than the rest of the dark matter, which is only going gravitationally. So neutrino decouples first, and that free streams, and then baryons and gas, photons and gas, which is blue and the red line, they closely follow each other for some time, and then at some time your plasma is cold enough that photon and gas decouples, and the photon free stream, and then essentially just move away. So that's roughly what we see in terms of CMB after the decoupling. And there is an excess density of baryons at certain scale, and so whatever the time at which this decoupling happen, at that time there is an excess density of baryons at these scales. And so what happens now, gravitationally, dark matter is going to get pulled with the baryons. So dark matter will also have this excess density at these scales, but dark matter is also going to pull back baryon, and so this eventual over density of this scale is going to be much smaller than the real one. So this is a small, very small peak, and this peak is going to be both in the dark matter and baryons. And so that's the point. And so this is what we call Baryon acoustic oscillation. When I showed you in the first lecture this CMB matter power spectrum, this has several peaks, right? So it has first peak, second peak of different height. That peak is essentially related to the same physics, but appears in different way. It appears in terms of what you're seeing in terms of the photon itself, which free stream, so the red line itself, right? But when we are going to do in galaxy survey, we are going to see, we expect to see the same kind of peak in the galaxies as well as dark matter distribution, because both of them are tracing each other. Yes. So this is not at redshift 10. This is moving very fast. That's why I stopped it at redshift 10. But if you look at it, that it happens much earlier. It's close to redshift 1000, and then very quickly by redshift 40 or something, everything is already in the same phase. So baryon and but finally I stopped it at redshift 10, but it will continue to be roughly like that at all redshift. Yeah, so what happens once the photon decouples, now it's gravitational interaction between them. So baryons or gas pulls the dark matter gravitationally to this peak, and dark matter pulls back the baryon, and so they both becomes more or less the same. So that's why the dark matter traces, baryon is tracing dark matter, and all the galaxies which are going to form is going to form in the baryonic distribution, which is also tracing the dark matter. And so in the galaxies also we expect to see that kind of peak. Okay, right. So this is what, sorry, was there a question? Yes. Right. So the whole reason so first of all, all of this is, if you think about in terms of the co-moving coordinate, the whole reason this whole thing was expanding is because of the photon. Once photon gets decoupled, there is no reason for it to continue going, unless in the late time when you think about the dark energy, but that term doesn't matter because you're working in co-moving coordinates. So everything is scaled by the scale factor. And so there's no reason for this peak, or for that matter, if you think about a pair of dark matter halo or galaxy separated by a certain distance, there is no reason for it to continue moving away from each other, except the expansion of the universe. But the expansion of the universe, because of the dark energy, is something we are scaling it out, because we are working in co-moving coordinates. Because of the photon, because photon was coupled and photon was trying to escape, but then baryons is coupled to it. So they're escaping, but then they're interacting with the gas, and so they are oscillating with each other. And that's why it was moving. But once it's decoupled, there's no reason for it to continue to move like that. Okay, so now, so far whatever I've told you is sort of a stories or theoretical exercise, but you can actually see this in real data. And so that's what you see in this plot, but let me walk you through this a little bit. So imagine this is a galaxy survey where each dot is a galaxy and color indicates roughly how far they are. So we also know redshift of these galaxies. So just to give you a visual impression, their distance is indicated there. What you could do is you could calculate power spectrum, which is essentially you make a grid of density field in the universe, density field of galaxies. So you make a grid. At each grid, you can estimate what is the density or number density of galaxies. You can do the Fourier transform of this density. So you'll get the Fourier mode of the density, and you correlate those two things. So this is what it means. So you have the Fourier mode of the density delta k or delta k star, and then you correlate that, and that's what is going to be power spectrum is. This is pretty much what we are trying to do in the tutorial, but we are trying to calculate correlation function, which I'll also mention in few slides. Okay, which is a Fourier conjugate of the power spectrum. So this power spectrum, which from my cartoonish picture, it should look something like this, right? And this is what the measurement looks like. So you can see this part is more or less similar. So you can see the oscillation, but of course, here I've exaggerated the oscillation. This oscillation is very tiny. So if you'll not pay attention, you'll not even notice that there's oscillation. But these are very highly significant measurement of BO peak. It's the error on this is roughly a few percent, so a couple of percent. With a couple of percent precision, we can locate this thing. So the red points is the measurement from the data, and what you'll notice is that the error bars here is tiny. So all of these points have error bar, which you cannot even see on the plot, but you can see error bar in this scale. And so the reason for that, and we'll get to again to develop a bit better sense of error, what happens is that when you're looking at the small scales, you will have many different sampling of the small scales in the same volume. So you can put many different spheres of small size in the same fixed volume. So that's what we call mode counting. So you'll have large number of modes at small scales. And so typically error on these kind of measurement goes with the number of modes. So the larger number of modes, you have a smaller the error is. Whereas when you look at the large scale, which means a small k, you're going to be able to have fewer independent number of modes. And so when you have fewer modes, then you have error is larger, so you can already start to see the error bar here, but you don't see error bar here. And this is all of this is a log plot. Okay, and so the red points are the data. This side of the plot is limited by the volume of the survey. So if I want to go to the larger k, I need to do bigger volume survey to be able to measure those things. This side is limited by the number density of your sample. So the denser sample you measure, the better errors you're going to get in this side of the thing. And the white line is actually our model. Okay, so white line is our model, which more or less goes through the data very precisely. But there's a fudge factor here, which we already talked about a little bit. If you were to predict what will be the dark matter power spectrum look like, basically something equivalent of this for Planck cosmology, then you'll find something like this. So that is the dashed line. Black dashed line is our model for the matter power spectrum at this redshift. But what we find is that there is a constant factor which you need to multiply, which is roughly factor of 4. If you multiply by a factor of 4, this model will become this model. And so in fact, that's what I've done. I've multiplied this by a factor of 4, and you can see this is on top of each other. It's not exactly factor of 4, roughly 4 point something, but just for the purpose of this thing. So what is this factor of 4? Anyone have any guesses? We have talked about this. So the power spectrum of galaxies and the power spectrum of matter will be related by something. Galaxy bias, yes. So galaxy bias. So this factor of 4 is essentially square of galaxy bias is what we have discussed, right? So you need to be able to essentially model these things, you need to have a galaxy bias depending on what kind of galaxy you're going to look at, and you can measure that directly independent of cosmological parameter. You can measure cosmological parameter as well as galaxy bias. And so for this sample, galaxy bias is roughly 2. So just to revise what we talked about already, right? Yes. Mhm. No. So this is the power spectrum for, let me see, this is z equals to 0.55, I think. So this galaxy sample which you are looking at is from something called CMAS data, which has a mean redshift of 0.55. Now, the question of galaxy bias change with Z, since we have measured these galaxies at redshift 0.55, we are measuring bias at 0.5, we are predicting model at 0.5. Now, if you were to measure galaxies at redshift 0, then are you going to be able to measure the same kind of galaxy? If yes, then how do you measure the same kind of galaxy? Then only you can talk about change in bias. But in principle, let's say if you take same, like from the theory point of view, let's say we are thinking about halo bias, which is the same kind of idea as galaxy bias. And you say, okay, there are dark matter halos of some mass, let's say 10 to the 13. What will be the bias of a halo of 10 to the 13 would look like? Now you can talk about evolution. And so what you're going to find is that this is going to change with time for two reasons. One, the whole density field you're talking about, the dark matter itself is going to accrete more matter. And so it's going to change its mass. And so if you look at the 10 to the 13 halo at redshift 0 and 10 to the 13 halos at redshift 0.5, they are actually not exactly the same halo. What is 10 to the 13 at 0.5 might be something like 8 times 10 to the 12 at, what is 10 to the 13 at 0 might be something like 8 times 10 to the 12 at redshift 0.5. So you're looking at different kind of halo. At the same time, this is relative to the dark matter, and dark matter itself is growing, right? So the whole density structure is growing. So there's a growth, which is what we measure as a function of redshift. And so both the denominator, the dark matter power spectrum amplitude, as well as the mass of the halos, you're going to like look at different masses, is going to change with redshift. Okay, so let's just revise this a little bit once more because it's a very important idea for if you're looking at galaxy surveys. What our picture is that in universe there are these collapsed region dark matter halos. So you cannot see this. I'm showing it as in the form of curvature, right? So which is there's a lot of mass, which is what introducing this curvature. And within this dark matter halo, there are many galaxies of different kind living in, which is emitting light, and that's what we are observing, and that's what we are tracing. So dark matter halo is expected to essentially form at the peak of the dark matter density distribution, and those are the good site for galaxies to form. So if you look at the over density, which I had defined as density over the mean density -1 of any kind of a species, the over density of peak will be related by over density of matter by a factor of bias, and this bias will be function of mass if you're thinking about halos. So massive halos will have larger bias, less massive halo will have lower bias. And so why is it function of mass? Because if you remember in my drawing when I did last time, if you have some density field of various heights, then the highest one is also going to form the most massive halos. And so when you change this threshold at which you are looking at these things, that is going to give you a different realization of the peak. Right? So if you go to a lower threshold, you're going to get different realization peak. Now you're looking at even smaller peaks. These smaller peaks will have smaller masses, and then the amplitude which you are going to calculate in terms of the overall clustering is also going to be function of mass. this is also why different galaxies have different bias, because different galaxies are sampling different halos. They're living in different kind of halo, or distribution of halos, effectively giving you different mass bias. So if you know your what kind of halos your galaxies are living in, you can actually predict what the bias is independently. Yes. So what do you mean by selection bias? Why would that happen? Yeah, so peak at Redshift is fine, but it will not be, typically the way it works is that you're only able to look at all the galaxies above certain brightness, which is different from being able to look at all the galaxy at certain brightness, right? That's the statement you're making. So there's going to be a luminosity cut, and that luminosity or brightness cut will translate into some sort of a halo mass cut. So you don't have any, sort of bias in that case. All you're saying is your threshold is different. You can translate that threshold, and that will not matter. But that's not entirely true. When we do these kind of surveys, we also have to sort of select these galaxies beyond just looking at the flux, which I'll come back to in a later. Right? In that case, there can be additional things. You are actually looking at some special regions of the universe. And so in that case, the bias is still going to be fine. You can calculate the bias. But since now what we are saying is that we have the dark matter density field, but we are sampling it in some specialized way. We are not sampling the full dark matter density field, and we are looking at the power spectrum of that. All this linear bias relation I said is basically, I said it's only a threshold you're applying and nothing else. But if you're applying not just a threshold, but you're also saying that, okay, I'm only looking at the voids, or I'm only looking at the cluster region, then this may not apply. And so then you'll have there is this idea of assembly bias. So if you have these kind of additional bias terms, which are called assembly bias, then you can bias your cosmology. So we put in a lot of effort to make sure or understand these kind of effects when we are trying to measure bias eventually for a real survey. All right. So yeah, so again, just to highlight, this is only in linear regime, right? So, but this is not going to be true when you have higher atom, when you have overdensity of order 1 in nonlinear scale. And so in principle, this BM will be function of K, and this K function of K could also be because of the special selections we might be applying to the samples you are looking at. And so it's very critical to understand where this K dependencies start and where you can assume it to be K independent. And in fact, you know, a lot of effort and work goes in. So often you'll hear that these surveys takes years to analyze. So what are the kind of things people spend time doing? Because measuring power spectrum, doing the survey, all of that is already you have established. Even after collecting data, why does it take years to do the analysis? The reason is that for each sample, you have to understand details like this. What is the B of M of K dependence, and in what regime you can use it without biasing your cosmology? What are your selection effects? And so this is actually a lot of people are actively working on a problem like this. Okay, so now let's move on to from our power spectrum to the configuration space picture, which is what we are trying to calculate directly and make an intuitive picture about that. So you can take your power spectrum and do a Fourier transformation, and you'll get correlation function. So this is again something we have already defined, and this is, it's not a bad idea to repeat. So now in place of Fourier space over density, you're going to correlate real space over density at x and x plus r, and that's what we call correlation function. You can do it at the level of overdensity or do it at the level of single galaxies, which is what we do in real observations. And you're going to get a plot like this. So this is same sample where we have measured correlation function. You see this. Do you see BO in this? Any guesses how would BO, which is this kind of oscillation, would look in this space? Just one peak, right? Yeah, that's good. Why? Because Fourier transform of a monochromatic sine function is a delta function, but this is not exactly monochromatic sine function. If there's a width, then it's going to be look like some kind of peak with some broadening, right? So that's what we expect to see. Sorry, did somebody say something? No? Okay, I heard something. So do you see a peak here? So you already know the scale at which you expect to see the peak, right? It's roughly 150 megaparsec or 110 megaparsec over age. Do you see actually this is the scale I already showed in previous slide. Do you see a peak here? Do you think there's a peak there if I zoom in? So there's a peak there, but you have to zoom in. It's a very small peak. It's a tiny peak. This is just a zoom in of the same plot. You can see the y-axis is 0 to 4, it's 0 to 0.02. The peak is 0.005. Right? So the peak is very small. One of the reasons why peak is small is the fraction of baryons in the universe is small. Right? If you change the dark matter density on baryon, let's say the total matter density is 30%, but I make dark matter 15% and baryon 15%, the height of this peak is going to increase because that's what is tracking this. And so in principle, you can measure the height of this peak and talk about what is the baryon to dark matter ratio. But that's not done because of some other reasons. But you can also look at the location of the peak, which is also very important because that's a fixed, well-defined scale. So when I talked about angular diameter distance, I said there is a well-known scale. If you can measure this across the universe, you'll be able to constrain dark energy because that will give you distance distribution, and that's the location of this peak. So the peak is tiny, but despite that, we are able to measure this very well. And just to repeat this idea, which you're trying to do this in tutorial exercises to measure correlation function, what we do here is that we find the pair of galaxies as a function of distance. We find the pair of random, subtract -1, and that's equivalent to doing this. And this is what the correlation function is. This is what we are plotting. Mm-hmm. Yes. Yeah. So let's talk about a few things before I answer your question. First of all, I have told you several times by now that we always compare pair of objects to pair of uniform random distribution. Any guesses why that is the case? So yeah. Yeah, so it's over density, but also because what we understand the initial perturbation in the universe, this is how you can calculate volumes essentially, right? So if you have uniform density of sample, if you at the same density, in terms of the over density is essentially number of objects divided by volume. And so volume, if you are doing a Monte Carlo way to estimate volume, what you're going to do is throw a random number uniformly distributed, count how many of them are within your whatever specified region, and that will, if you multiply that number to the density, you'll get the volume. So that's why it's done that, and so this is a way to calculate this over density. Now, what's going to happen is that also what we expect that universe is fairly close to uniform Gaussian random number, uniform Gaussian distribution in the beginning, right? So that's what I started by saying, that the initial condition of the universe is fairly close to that with some specific power spectrum. And so that means that at large scale, you do not expect any clustering. So your correlation function is 0. So these two things are same. And that's what you see here when I plot it in this way. But then at small scales, it increases. That is because of gravity. So what is going to happen is that at small scales, things are going to start forming and collapsing at different radiuses. And so if you have two overdensities, and let's say these are the only overdensity in the universe, they are going to fall under each other gravity, and they're going to come and collapse. And so things are going to start clustering at small scales, which is why this is going to start increasing. And when you go to very small scales, when you go to the scales of the halo, you are going to start seeing what is the density profile of the halo itself in the correlation function. So if you go to smaller and smaller scales, it's going to higher and higher. At some point, Depending on now what kind of dark matter physics you're talking about, there might be a core of the dark matter halo, there might be self-interaction, there might be warm dark matter, and all those things will also start play a role in terms of what happens to the behavior to very small scale. What is the minimum mass of the galaxy? In this sample? So you can, under some assumption. So what you can say is that you can, first of all, by looking at the bias, you can figure out what is the mean halo mass of the galaxy you're looking at. Now, if you have the mean halo mass and you assume that the light to mass ratio is something constant, or galaxy to halo mass ratio is some constant number, which is going by the baryon fraction, you can estimate the mass of the galaxy. But that's not very accurate, because all the hydrodynamics and everything is not going to make that always constant. It will depend on what kind of galaxies you're looking at, whether you're looking at star forming blue galaxies or galaxies with active black holes, and all that is going to play a role. But to first order, you can do that calculation. We often do that. We can calculate mean halo mass, distribution of the halo mass of these galaxies hosted by, as well as estimate some rough mass. But a better estimate of mass of galaxy is something you can get by modeling the galaxy spectra, which I already showed you. So for all of these galaxies, we already have spectra of these galaxies. By modeling the spectra, you can estimate what is the total mass of the galaxy, and that will be much more accurate number. Okay, but if you have seen any BO paper before, you have not seen this kind of plot, right? Or even this, what you must have seen is this kind of plot. So it's nothing different. It's the same correlation function. All I've done is multiplied y-axis by s square. And so the reason for that is there is an overall drop in correlation function. And this is, if you plot in log-log, you'll basically see a slope. I've plotted in linearly, so you don't see a slope. And that slope is roughly -2. So if I multiply by s square, you're going to essentially overall get a scale-free correlation function, and you'll see all the additional feature. You'll see what happens at small scales. For what happens at BO peak, you're going to see the peak in much more enhanced way, but the error bars also increases. And what also I'm showing here is the location of this peak, this dashed line. This is what we call standard ruler. So this is something we can predict. For this particular sample, this was measured to 2%, so 1.8% is what I'm. So if you do the formal analysis of this and figure out, okay, where is the peak of the location of this peak with respect to lambda CDM model, you're going to find that this is 1 plus minus 0.02. So it's a 2% precision measurement, which is actually very precise. Now we are planning to do BO measurement to sub% precision, so less than 1% precision to improve. So delta RBA, what we are trying to do here is that in place of calculating the absolute location of the peak, we are saying, okay, we know in lambda CDM picture, if you take certain cosmological model, Planck or slightly different from Planck, what is the location of the BO? And so if you know that, then what we are trying to measure is that how much is the true measurement deviant from that. So you're taking the ratio of that. In this way, it's easier to sort of look at the error also. So it's basically one means it's consistent with the lambda CDM exactly on top of each other. In fact, in this case, with a plus minus 2% error. So what would change in future surveys? So how would the peak shift if you want to do a sub-percent? No, so when I'm saying sub-percent, I'm talking about the accuracy, right? The peak may not do not shift. It's the accuracy of the peak. So what does accuracy of the peak depends on? It depends on what is the amplitude of this, and it depends on what is the error bar on these individual points, right? Both of these. So what we can control in principle, we cannot control this amplitude because there is a given baryon to matter ratio in the universe. So you cannot do much about that. You can do slightly by selecting different kind of galaxies, and so that will have different bias, and all of these scale with bias. But you can reduce the error bar on these points. If you reduce the error bar of this point, your measurement will be more precise for the BAP. So that is what we like to do. Hmm? Yeah, so this is a very good question, and that's also a warning. Whenever you look at this kind of data, what you have to realize is that we are very used to doing chi by I. So basically, we look at this and we say, oh, this is 1 sigma, this is roughly 2 sigma, this is 2.5 sigma, and there's a deviation. So that's not a very good thing to do for this kind of thing. You can do that in power spectrum space, by the way, but not in correlation function. The reason for that is when you look at the power spectrum, the modes are very more or less uncorrelated at the scales of BU. And so you can say that whatever this error is good enough. But when you look at the correlation function, there's a significant cross covariance term, which means these points are not independent. They fluctuate with each other. And so even if this is a deviation, if you look at the best fit chi-square, when you account for this covariance, the fact that these points can move in a correlated way, if you account for that fact, then you're going to find that it's a very good fit. Yes, Naveen. What causes the? Yeah, so the covariance for the data point can come from various ways. Some of this will be because of how the survey is done. So let me not talk about that. But it also can come because of the physics. So now what is going to happen is that it's one same scale, but it's oscillating, it's higher, which is physically related. And so because of this physical correlation, your nearby modes are going to fluctuate together. And so that's what causes a cross covariance term, right? In the sense that what I'm saying is this and this is not independent. Those two scales are not independent. It is going to matter what is happening here to the scale. So if there's a shell, imagine one shell. If you think about the one shell moving inward, so somehow the broadening of the BO because of whatever the velocity dispersion is happening, it's going to matter what is the density in the inner shell and the outer shell, and so they are all correlated. Whereas when you write this in the Fourier space, you're talking about different modes, and the modes are decoupled, and so the same kind of thing is much less correlated. So which is why it works, which is why you didn't see such discrepancy in the power spectrum. It looks. Yes. Whether you can call it 1 by q1, because it's not just 1 by q1, it's integral over all the k. Any r is integral over all the k. And so that's not evolving independently. Mm-hmm. You mean this thing? If you take the larger volume, by feature you mean BA or this thing? Yeah, this one. Yeah, so since this is a fluctuation, if you take a larger volume, what is going to happen is that the errors are going to reduce. If error is smaller, then this kind of deviation will be significant. So we don't expect something like that to happen. If your model is accurately describing this, then even if there is a deviation, it will be smaller. So that is something we expect to happen, but I can't predict what is going to happen when you actually do that. Right. So I guess now you know basically how we do all the steps to measure BEO. We start by galaxy survey. You choose a telescope. You figure out what kind of photometric band you want to choose. You do very precise photometry, which means you know the locations of these galaxies very precisely in the sky. And so that has to be very accurate. And once you do that, the difficult part is to get the distance. For typically BA survey, we try to do spectroscopic redshift, but you could also do nowadays narrow band filter, which I mentioned, and that will give you, so you'll observe a spectra, either very large R or you'll observe with a smaller R, so you'll observe 40 bands. You'll look at various lines and then finally figure out, okay, what is the scale factor at which this thing was emitted by looking at the location of the line compared to the observed location, and that will give you redshift. So this will give you redshift of each object. Now you also have RA-Dec. Now assuming a cosmological model, you can calculate distance to this thing. And so you do not need to. So yesterday I sort of Taylor series expanded A of t, but you do not have to do that for real analysis, and you look at the full form of what the A of t should look like. So that will give you, yes. Mm-hmm. Depends on what kind of galaxy survey you're doing, right? So as I said yesterday, you can do galaxy surveys, you can do photometric galaxy survey, which is broadband photometry. You can do it in one band, 3 band, 5 band, whatever you want. You can look at it in different wavelength bands. You can do narrow band photometric survey, which means 40 or 80 band. Spherix is going to do 400 band. Or you can do full spectroscopic survey. So you can do all 3 of them depending on what you want. So for the BO results I showed, these are all from a spectroscopic survey. So these are from SDS, Sloan Digital Sky Survey. So now, sort of like just coming back to the same idea, this standard ruler is understanding what this standard ruler is fairly important, and we can predict what the size of the standard ruler is basically how far universe is expanded till the recombination when photons start to free stream, and then we start to see that the baryon peak is there, which then captures dark matter as well, and the dark matter pulls back baryon. So this is something you can calculate, but it depends on knowing a few details. For example, you need to know when the recombination happened. You need to know what is the scale factor of recombination as well, right? So just the galaxy survey do not have information to actually measure this directly. Right? All the BO scale you are going to measure is a function of this scale, and this is what we also call as LBAO is also called as sound horizon. And so every time you're going to do a BO measurement, it's a standard ruler up to the factor that you know what is the sound horizon. If you don't know sound horizon independently, then you're only measuring ratio of sound horizon to whatever the BO scale is. And that's important information, which is why if you just use BO survey, you'll not be able to constrain cosmology very well. You need to use CMB information, or you need to use at least sound horizon information somehow. So you can use sound horizon either directly from the CMB data, you can use BBN, Big Bang nucleosynthesis model, and that's also have very precise sound horizon. So either way, you need to use that information to constrain things precisely. E spectra will also give you this horizon, but the TT is the most precise one. Once you have it from TT further, you don't care because you don't improve on top of what TT will give you. Okay, so let's get back to the idea of precision for BO. So how do you make the error bars I showed you smaller, right? So it seems like the natural thing to do is measure lots of galaxies, do a bigger survey. You have large number of galaxy spectra, and so you'll have 3-dimensional position of large number of galaxy. We can measure clustering, and that will be it. You'll have smaller error. But will that be the optimal thing? And how do you select the galaxy? Do you have to select galaxy first of all, or you can just measure everything? And the problem is that you cannot measure everything. So this is an image which I also showed you in one of the previous slide in a slightly smaller manner. This is from something called Legacy Survey. Legacy Survey is a 6-year campaign of photometry. So they did photometry in G, R, and I band, and I hope all of you now understand what that means. So you basically image the sky in G, R, and I, these 3 optical bands. And we also had data from WISE telescope in W1, W2, W3, and W4 bands. So this is an image from a survey like that, which gives you something like 1.5 billion galaxies and 1.3 billion stars. If you look at the data, this is observed through 3 different telescopes, and you have like really large amount of data. And this is nothing once LSST will come online, right? So this will be completely dwarfed very soon. And it took 6 years of data collection plus a couple of years of processing to get this. Why do you care about this? If you want to do a spectroscopic survey, what you have to do is you have to figure out where to put the fiber. So for a spectroscopic survey, if you remember, you have to take the spectra of a single source. So you have to take light from a source, pass it through the spectrograph, gratings, split it, and then observe it. So to do that, you need to first know where the source is. In a spectroscopic survey, you cannot directly know where the source is. You have to first do a photometric survey, figure out where other sources are. This is why this survey was done. The survey was precursor to DESI. It's also called DESI Imaging Survey, or DESI Legacy Imaging Survey. And so what we did is we looked at this, all the catalog of 1.5 billion galaxies, and then you have to figure out, okay, what are the galaxies you want to observe its spectra. Now, why do you need to select that? Can you observe a spectra of all of these 1.5 billion galaxies? Let's try to take a look. Right. So for BAO, we need the spectra of galaxy because we need precise distances. Now, DESI has 5,000 is optical fiber. So what happens is that you have to take the light and you have to align optical fiber exactly at the location where the light from galaxy is going to come in the focal plane. So that's a hard job. There are robots in the focal plane which does this. And through a survey like this, you already know what is the location of the galaxy. When you go and observe, you want to go and observe a spectra, you already know what are the galaxies you want to observe. You ask the robots to align itself to exact location, and it has to be very precisely, otherwise it's very easy to miss a galaxy. You can see these are all tiny dots, and in focal plane also they are tiny dots. So what happens is that in DESI there are 5,000 such fiber, and so you can measure 5,000 spectra in one go. This is the largest number of objects you can measure in one go so far. The previous big number was SDSS could measure 2,000 spectra at a time, and before that it was in hundreds. So these are called multi-object spectrographs. So you can observe multiple objects at the same time. If you go to any big telescope, they can observe only one spectra at a time. So they have only one spectrograph at a time. Right, so DESI can do 5,000. There's another experiment called Foremost, which can do 4,000. And there's something called PFS, Prime Focus Supreme Cam, Prime Focus Spectrograph, which I think also of the order of 4,000. And those things are also happening. So you can think, basically generalize all the things I'm talking about for those cases. What is same redshift? No, so this is not 5,000 galaxies, it's just 5,000 fibers. So you can measure 5,000 spectra of whatever galaxy you want. So far there's no galaxy in it, right? So you can assign it. So these galaxies could be any redshift. We don't know the redshift of them. We know photometry in 3 bands, so we can guess what might be the redshift to some precision, but that will not be very accurate. But that is something we use, in fact. But what I'm saying is that once given this map, you can make 5,000. You can measure 5,000 spectra at a time. Now, you also need to think about time, right? So we want to do this survey in 5 years because we don't want to keep doing this forever, and we want to try to aim to do something in 5 years and see what kind of improvement one could get. So often what happens is that a fraction of fibers do not work, don't go to the position. Some of them are used for stars because you want calibrations, you want to figure out what are the atmospheric lines and all that, so that you will be able to clean the data later on. And so let's say you are using effectively 4,000 of them to measure actual galaxies in your cosmological survey. You observe roughly 8 hours in the night. These are all optical surveys, so you cannot do once the sky becomes bright, then you cannot observe and efficiency goes down. And let's say you do 2 per hour. So you basically, means you expose each time 30 minutes. So that's the exposure time for DESI for dark time sample. So you do 2 of such sample per hour, you are going to measure 64,000 spectra per night, which itself is actually a very large number. Before DESI, you can't imagine. It will take, it used to take 5 years to do something like, in a previous survey like Gamma, 300,000 spectra took 5 plus 6 years to get 300,000 spectra from before DESI. So you can do 64,000 spectra, which is already a very large number. And let's say if you do that for 5 years, 365 days, 5 years, and of course there is always an efficiency factor in the sense that there are bad weather, there is summer, you need to clean up, recoat your mirror or do this and that. And so this is roughly what it looks like for instrument like DESI. So you'll be able to measure 58 million galaxies. So that is the number you can measure with this kind of instrument and this kind of efficiency in 5 years' time, which is already very good. But we have 1.5 billion galaxies. So out of 1.5 billion galaxies, if you measure 58 million, it's roughly 4%. So how do you select which 4% you want to measure? So that you'll be able to do a BO analysis as one of the prime science case and improve constraints on track and education of state better than what has been done before. Yeah, so that's a great question. The exposure time ideally for any telescope will depend on, the first thing is it will depend on how big your collecting area is, right? So the bigger the collecting area, more light you can collect, the faster you can get to what we call 5 sigma. So enough to detect, you need to collect enough photon that you are able to detect the galaxy confidently. So how big your collecting area is. The second thing is once it collected from the collecting area, it goes through your instrument, and the instrument have lots of loss. We talked about quantum efficiency. So let's say whatever your quantum efficiency is of the detector versus the light has to travel through all the different components of the instrument, in this case of fiber, how much fiber get lost. So this is what we call throughput of fiber or the instrument. It will depend on that. Once those two things is fixed, so for a given instrument, let's say those two things are fixed. Now it will depend on what is the light coming from, like what is the flux of the light coming from the object, right? So once you have said that, okay, my collecting area is this much, my throughput is this much, and I can detect photon with this efficiency, you know how many photon you need to collect. Now, if you know the flux from the source, you should be able to predict how long you have to expose, because that's the number of photon per unit time per unit area you can predict. So it will certainly depend on the luminosity. And so when you're trying to select this 4%, you also want to be fast. So I've set this 30-minute. You want to select the kind of objects you will be able to do that in 30-minute exposure time and confidently detect it. And so the easiest thing will be to select the brightest object, right? So whatever I can select 58 million brightest object, and I'll do the spectroscopy and measure this. But that will not be very useful. The reason for that is the brightest object will be closest to you, and you'll have many of them. So you can easily select 58 million, and you will not even reach redshift of 0.5 or so. There will be some objects at high redshift as well, but most of it will be dominated by very low redshift. And so if you have low redshift, I have mentioned volume is one of the important factors, right? So think about a spherical shell around you. And as a function of distance, the volume in the spherical shell is going to increase significantly. If you are at very low distance, your volume is very small. And so you may not want to do that. That's why all the complications comes in. So you need to be confident that the exposure time you are sort of setting as an upper limit is good enough to detect the galaxies you are selecting, and those galaxies are distributed in a manner that gives you optimum measurement precision. Right, so how to select 4%? So that brings me back to the idea of how does the noise and the error propagate in measurements like this. So if you think about signal to noise, you can also do Fisher, basically you can apply all of this and do a Fisher forecast for that. What I showed yesterday is that I already assumed the precision of BAO, and then what will be the forecast for the cosmological parameter. You can do now, you can say, okay, if you assume certain characteristic of the survey, what will be the precision errors on the measurements like power spectrum, and then once you have done that, now you can do the same kind of derivative exercise to figure out what will be the precision of BAO. So this is what is done for DESI before deciding on all the numbers I'm telling you, all these quantities. So what you're measuring is essentially power spectrum, and the signal to noise will be power spectrum divided by square root of covariance, which is essentially the standard deviation in a situation where there is no cross covariance term. Now, I've already showed you, given the current understanding of universe, the matter power spectrum amplitude is this, the galaxy power spectrum is this, and so if you are measuring galaxies which are most likely fainter than this, the bias will be slightly smaller. Bias will be smaller than this, not bigger. the deeper you're going, the fainter galaxy you're observing, it will be residing in lower halo mass, the bias is going to go down. So all future survey, typically bias will go down. And so this is the range in which the amplitude of the power spectrum would look like, roughly at k of 1. So 10 to the 3 to 10 to the 4. So you know roughly what is the amplitude of your power spectrum itself is. Now if you can estimate what is the error, you can sort of see what kind of things will be important. So this is not exact for nonlinear scale, but it's a very good approximation for linear scale, and BO is mostly linear scale. Although even for BO to do precise analysis, you have to do something more carefully, but in a Gaussian random field, this is good enough to do this kind of exercise, what we do. So for a Gaussian random field, you can calculate how does the variance of the field look like. So you basically write down the Gaussian random field and you calculate variance, which is field square average minus field average to the square, and that will give you variance, and that variance would look like this. So there are important term is there's a power plus there's a short noise. So where n is the number density of the object, right? So there's a term called power plus short noise, and there's a term for volume. So this is the effective volume of the survey you're looking at. And all of this comes from essentially the mode counting exercise. So this is the mode counting, number of modes you're going to look at. So what you want is you want essentially sigma k to be as small as possible. So you want to minimize sigma k, and hence if you want to minimize sigma k, you have to maximize volume, and you have to essentially minimize this term, p plus 1 over n bar. So when we say short noise is independent of distance. Typically, when we think about short noise, if you look at the power spectrum of the short noise, it's constant. So this is constant, but the power spectrum of the galaxy is not, right? So when you add these two things, there might be regime where, let's say, short noise is at this level, then there is all these scales which is below this scale, its power spectrum is larger than short noise. All the scales above that scales is going to be, short noise is going to be larger than power spectrum. And so depending on, and we know BAO is roughly 110 megaparsec over H, roughly K of 0.1 to 0.2, you roughly know the scales what you want to optimize for, right? You may not want to optimize for all scales, but you want to roughly look at the scales at which your physics is relevant. And so these two things are going to, in fact, decide how to improve things, right? And so that is basically the main point I'm trying to derive. If your short noise, your power is sort of fixed. You don't have much control on the power. Given how the universe is, that decides your power. You have a little bit of control by selecting different bias of the galaxy, but that's within this range. You cannot lower the power below this, and you cannot have higher density and increase the power above that. So your power is more or less fixed, you can't do much about it. And so you can ask, okay, given this power is fixed, what is the number density this correspond to? And so at that number density, if I have even the higher number density, I will probably not gain anything. So if you ask yourself, when your short noise is smaller than power, which is basically that will give you number density bigger than 1 over power, that's this. So if you have sample of galaxies, which is roughly 10 to the minus 3 to 10 to the minus 4 in terms of number density, then at that time, your short noise is going to basically subdominant. If you have higher density sample, even if short noise is going to reduce, it's not going to help because this term is going to start dominating. And this term you already know roughly what the range is. So in other words, if I want to sort of minimize this error, once I get to this level of number density, increasing it further doesn't help me. Okay, at least for these scales. And so the optimum survey will be where you are able to achieve an inverse of the power at relevant scale for BU. And so you want to, rather than selecting all the galaxies in local universe, you want to spread your sample across, and that will also give you large redshift coverage, but such that you always have this kind of number density which is related to the power you expect for the sample you're looking at. So if you know roughly the bias of the galaxy you're selecting, you know what the number density you want to target. And then you can spread this 58 million galaxy across redshift, which will give you much better constraining power. There's no point of going anything better than that. So this is what this thing looks like for DAISY particularly. I've already showed you this plot. DAISY has generated various kind of sample motivated by exactly what I told you. So you can do bright galaxy survey. So these galaxies can be observed in 5 minutes, essentially. So DAISY only expose things for 5 minutes when it's looking at BGS, which goes up to redshift of 0.5, and you already have more density than you need. It's actually much more dense sample than you need, that requirement I have set, right? Then you can go to higher redshift and you can measure these what are called luminous red galaxies. And you can go to even higher redshift and you can go observe this emission line galaxy which have this O2 doublet. And you can go to even higher things and measure quasars and Lyman alpha. So why this sort of a strange kind of thing? The reason for that is the exposure time and our instrument. So we can measure these things for 5 minutes. These are fairly bright galaxies. These are living in 10 to the 13 halo mass or so. And so they're bright enough that you can measure them in dark time in 30 minutes. Now beyond this, there are these galaxies even beyond this. But if you try to measure them, it becomes very difficult. Your signal to noise doesn't really have good enough. You need to expose them for long, and so you don't want to do that. So we sort of stop observing these beyond redshift 1 or 1.2, something like that. And so what can you do? So you can do these, observe this emission line galaxy. What is the interesting thing? They are star-forming galaxy and they have very bright O2 doublet. So most of the time you don't even detect their continuum. You don't see much of the spectrum, but you see this O2 doublet. And since it's O2 doublet, and that's important because it's not just one peak, there is a 2 peak attached to it, which means it can be uniquely identified. Because if you have just one peak, you will not know, and if you don't have anything else, you will not know which line it is. So how do you measure redshift? That will be a problem. But it's a doublet, so if you just measure O2 doublet and you don't measure rest of the spectra, that's good enough. Which is why the noise is very flat. It's mostly the noise response of the spectrum except the O2 doublet. And that is something you can do in 30 minutes and still go beyond redshift 1, and that goes up to redshift 1.6. At 1.6, this O2 doublet essentially fall off our spectrum. You can see it's at the corner. If you go to further redshift, it's basically be in a very noisy regime and we cannot measure it. So you stop at 1.6 measuring this. So beyond 1.6, you can only measure these supermassive black holes which are active at the center of galaxy, what we call quasars. And so we start measuring quasars. We start measuring quasars already from redshift 0.8, but I'm only plotting from here. These are much sparser sample, and then you can go up to redshift 2.2, at which point you start seeing Lyman alpha forest, right? And so you can measure Lyman alpha forest and go up to 3.2. So this whole thing is essentially decided by, okay, what can I measure efficiently and how to spread it and what is the good number density. Now, taking this picture and come back here. So this is redshift, and that's the percentage error in BEO we think we should be able to measure it. What this white line shows is if you were to do a 14,000 square degree and say your error is dominated by cosmic variance, which means short noise doesn't play a role, short noise is subdominant, which means you have sufficient number density, then this is the line you're going to observe. So if you measure more dense samples, it's not going to help you. You'll be limited by this line. This is what we call cosmic variance, is limited by volume, right? So the noise has a volume term, and that volume term multiply depending on the power amplitude of the power spectrum, that's what limits your noise. You cannot do anything better. You really have to go to higher redshift to do better. But this gives you 5% at very low redshift because it's very low volume, and at high redshift the volume is larger and larger and you go to sub% precision. But this is the best possible case. This is what, given these definitions of the sample, this is what we think DAISY will achieve. So DAISY will be cosmic variance limited at small redshift, even with 5-minute exposure, because it's very easy to observe these things. But we are not able to go to cosmic variance, which means we are not able to achieve this number density but we are fairly close. So it's 1% versus 0.5%. We are fairly close in terms of the LRG. We are not there in terms of the ELG simply because the number density, like exposure time constraint, if you want to observe more ELG, if you want to have denser sample here, you need to increase your exposure time, which we didn't want it to do. So your error degrade. And then when you go to this kind of quasars, they are very rare, very sparse. They have number density of 10 to the minus 5. So 10 to the minus 5 is order of magnitude smaller than this number density I'm targeting, and so your error blows up to even further. So this is what we expect B error look like after all the optimization we have done, if we can measure 40 million spectra of the things. Another thing which I'm not going to talk about, but you should think about, okay, I've very easily said, okay, these density of this kind of thing, but before measuring spectra, all you have is photometry in 3 band. So how do you go about and actually select these samples and these redshift bands and things like that? And so the way you do it is basically you try to use all different combinations of photometry, and you try to use a subsample of the galaxies where you do have a spectra from other surveys or previous analysis. And then based on that, you estimate photo Z's and then try to detect this. And then you, before you start the survey, you also do a phase which is called science verification, which means you're going to observe each of these class of target and see whether you're able to get good enough signal to noise, you're able to measure redshift or not. If not, then we redefine things, you readjust things so that your efficiency is high, which is what is done for DESI. So this is the forecasted thing. The actual thing is slightly different because everything didn't work as we planned. And so the actual thing will be slightly different from this, but this is what is there from the forecast, is what I'm showing you. Beyond Redshift 2.2, yes. Yes. So this is not the spectroscopy versus photometry, right? The error is big here. First of all, this is not Lyman alpha. I'm stopping right where Lyman alpha starts. If you go further, then that's beyond 2.2, Lyman alpha will do. So that is one of the sample I'm not showing in this plot. If you include Lyman alpha, then you'll go up to something like Redshift 3.2. No, so this error purely depends on the number density. So since the quasar and the Lyman alpha have much lower number density, your short noise is going to dominate, and short noise determine the error on the power spectrum, and that's what will determine your B error. Okay, so right. So okay, now you have some understanding of how sort of we go about thinking, optimizing surveys like BO. I've mentioned DESI so many times, but I haven't really told you what DESI look like. Right? So let's just do that quickly, and I'm also running out of time. So DESI stands for Dark Energy Spectroscopic Instrument. It is the program, the first program which now known as DESI-1 rather than DESI, is a 5-year program started in 2021. We'll finish collecting 5-year data 2026. At that point, we'll have 40 million extragalactic spectra selected. This is the DESI Mayal dome. It's in Arizona, Kitt Peak. This is the DESI instrument. The whole thing about fiber and so all of this is actually very old. So this whole telescope is very old. This whole box is the brand new thing. This is where we have all the new instrumentation, and the spectrograph is in a room which is not shown in this image. So there are optical fibers and robots in this plane. So these are the robots. So this is the focal plane, which is here. And there are optical fibers. All of these are optical fibers which collect data, and the optical fiber goes through the telescope and go to the spectrograph where we measure spectrum. Okay. So we already have 3 years data which is being analyzed, and the expected plan is to measure something like 40 million extragalactic spectra eventually. Now, one of the remarkable thing, if you look at the previous survey, like the biggest survey in this kind of thing is Sloan Digital Sky Survey, measured something like 3 million spectra in 12 plus years of spectroscopy. And so the reason for that is, first of all, the focal plane was smaller. It was this is a 4-meter telescope. That is a 2.5-meter class telescope. So the exposure time had to be larger because the collecting area is smaller for each. But also, the focal plane, these are optical fiber which are being plugged into aluminum plate, which has to be done manually. So you have to drill hole each time you want to see a part of the sky. Let's say this part, you have to figure out what are the objects you want to observe today, and take the aluminum plate, align it, and then drill holes at all the locations of the galaxy. So if you hold the aluminum plate and look at the right direction, you'll see light coming out of galaxies at exactly the right location. You do that, and then you plug fibers at the locations of these things, and then you put it in the telescope focal plane. And so this was a very manual, laborious thing, and that was part of the reason why it took long time. Now what DESI has is it has a much larger number of fiber, but these are all robotically controlled. So they have 2 axes on which they can move. You can control them and align them where you want to. You don't have to do this kind of thing. There are lots of DESI aluminum plates available. If you want, you can order them actually. They can also ship it for you because they have so many of them. They have observed it for 12 years. Why is it? I don't know. I think that probably that was the cheapest, and because you have to use it just once and good enough to drill hole, but I don't know. They might have played with different materials. This one? So 3 years data should already, okay, I can't tell you the exact number. 1 year data was 6 million, 3 year data will be 18 to 20 million galaxies, give and take. Yeah. So the total will be 40 million. I think this is already ahead of schedule. So the full sample will probably be more like 25 million for 3 years. But in cosmology analysis, we never use full sample for various reasons. We'll use full sample when we'll do the 5-year analysis. But okay, I'll come back to that, why we don't use full sample, but 25 million roughly. So that's not with 3 year data, that's just with 1 year data. Yeah, so when this 3 year data, we had this 3 year data in April 2024, that's when the cosmological results were analyzed. That's when we analyzed 1 year data, because it takes few years to analyze the data. So now we are analyzing 3 year data and updating that result. But yes, so at 2.5 sigma, I'll show that also. 2.5 sigma lambda CDM is not favored, but it's 2.5 sigma. This 6 more months, you'll know what happens. This, of course, this can change because it's all about the confidence, right? It's all about how statistically significant you have detected an effect. And the claim right now is that it's not very statistically significant, but it's interesting. It's also analysis of not just DESI data, it's DESI plus supernova data. And so a lot of things depends on the supernova data. So when DESI data will become bigger in fraction in terms of the constraining power, we'll have to see how things shifts. So this is a closer look to focal plane, and this is one of the sort of big mess and big worry for us. Anyone who is doing this kind of analysis and collaboration, they have to worry a lot about focal plane. So how does the focal plane look like? There are 10 petals. Each one of these is a petal. So there are 10 petals. Each one of them have 500 optical fiber. So these holes are where this robot sits and holds the optical fiber. There are 500 of them in each one of them, and there are 10 spectrograph at the back end. Each one handles one of the petal. So 500 channel for the spectroscopy. If you zoom in like this part of the thing, this is how it looks like. So these things, this is the reach of a fiber. So let's say if there's a robot here, how far this robot can reach. You can see there's an overlap. The overlap is designed so that there are not lots of gap. The holes do not have overlap, of course, but the reach of the fiber from the robot has overlap, because robots have arms which can open up and go to further distances. So what is going to happen is that from this 1.5 billion galaxies, when you reduce it to something like 5 million, 50 million galaxies, you still have lots of galaxies. And so in a pointing of one optical fiber, you'll have several galaxies. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9. These are all the circles are the one which we are going to target. There are other galaxies which are not circle, which we are not targeting. So they're not part of they're part of the other 96% sample. So you can see within the reach of this one fiber, there are 12 galaxies. But one fiber can only target one galaxy at a time, right? Because you have to take one light from one source and do the spectroscopy. So what do? What you do is you basically cover each part of the sky in different passes, which means you revisit the sky. So you tile the whole sky, you look at one part, you go once, then you go to the other part of the sky and you'll come back to that part of the sky, but not exactly the same. You try to dither slightly. So it's like, this is my one pointing, this is what telescope is seeing, then it might see something else, and then it might come back and see an overlap like this. Okay, so this is pass one. Both of these are pass one. We call it passes, and this will be second pass. So another layer, and then there will be third pass. So on top of that, there will be third pass. So similarly, you visit each part of the sky multiple times. So given the tiling of DESI, we have two type of program. One is dark time. So in my spectra, there was something called BGS, which I said we can measure in 5 minutes. So that's in the bright time. That's basically just after the sunset and just before the sunset. That's, the sky is already becoming bright. Rest of all the sample measured in dark time. So dark time have exposure time of 30 minutes. Bright time have 5 minutes. So in dark time, we are hoping that we can sample each part of the sky something like 5 times. So each point in the sky will cover 5 times. We'll visit 5 times. In bright time, we'll visit 3 times. So by visiting 5 times, we'll be able to, so you choose one of them and observe them. When you visit again, you choose another and you observe them. You'll be able to observe more galaxies, right? But even if you visit 5 times, this is a dark time tile, you can see there are 12 of them. You cannot measure all of them. You'll measure only half of them, even if you visit 5 times that patch of the sky. And so there are lots of such dense regions. These are basically corresponding to high density region of galaxies, where we'll have missing objects. So we'll not be able to measure all the objects despite 5 years of survey, despite 5 times visiting that in our target catalog. And so this is a specialized missing, right? So somebody asked about bias because of the selection. Here is also a selection happening where in high density, you're not able to measure all the objects. And so how do you sort of correct for that and account for this is one of the big nightmare and big issue in this survey. There are algorithms. I'm not going to talk about that, but if somebody want to discuss, I'm happy to discuss that offline. But there are algorithms which tries to address this and mitigate this and see how to correct for clustering and measurements for these kind of effects, which are being developed and improved upon. And these are the kind of things. So these are the kind of things which takes time when you are doing analysis. You have to sort of basically track all of these kind of effects, and sometimes there are failures in terms of the measurement of the spectra itself. Okay, so it's very important to be aware that something like this exists if you're looking at DESI data, right? So you can't naively measure, just take the data and measure clustering, the kind of thing we're doing in tutorial. You have to also account for the fact that there are these fiber collision or limited fiber things. And so sometimes you're seeing fewer galaxies because you just didn't have enough fiber to see that. So you have to correct for that. And that correction needs to be applied before you measure clustering. Otherwise, your clustering measurements will be biased. Okay. So I guess I'll have to stop soon. Let me see. Let me finish this slide. So just to give a summary of what I've sort of walked you through today, after you already know details about various kind of measurement one can do in galaxy survey, for this particular example for DESI and for any spectroscopic surveys, the same thing will be true. You have to do something like 6+ years of imaging campaign with 3 telescopes, covers 18,000 square degree, measures 1.5 billion galaxies. You build DESI instrument with 5,000 optical fiber. Building this instrument itself took 10 years. One of the slowest thing is actually to smooth the lenses which is on top so that your field of view becomes bigger, right? So you have to make the field of view bigger for this kind of instrument. 10+ years, it cost 600 crore rupees to make DESI. So that's the cost of the whole instrument. And it's a collaboration of 700+ people working on this. All kind of people, engineers, scientists, PhD students, postdocs. Often a lot of work is driven by postdocs and PhD students in collaborations like that. Okay, now you need to figure out, okay, what are the objects you need to select. And so I told you about this idea of NP equals to 1, which means you want to just select roughly the number density such that your power spectrum of inverse of that and not do anything more than that with 30 minutes of exposure time. And that, so in the year 1 analysis of DESI, we got something like 6 million extragalactic object. And then you have to actually do a lot of computing, not just with the data, but also with for the theory and the covariance. So you have to spend a lot of time in terms of computing, estimating errors, and then realizations of these kind of fiber effects I told you. You have to statistically sample that and show that it's unbiased. And at the end of it, you get this. Right? So this is the result from DESI year 1 sample, where for each of the sample I've already told you about, BGS LRG has 2 bin, LRG1, LRG2, LRG plus ELG, ALG, quasars, and Lyman alpha. For each one of them, you can measure correlation function, so that's the point with the error bar. And these are all multiplied by R square, now you know. Right? So these are not just Z of R, these are R square times Z of R. And then you can see the models for each of them. All you're trying to do here is figure out what is the location of this peak for each of these sample. And once you know the location, you can convert that into angular diameter distance given, you can convert that into angular diameter distance within a factor of RD, sound horizon, if you know the sound horizon. And then you can plot this as a function of redshift. So these are the ratio of what is called dV over RD compared to lambda CDM. So if it was lambda CDM, what was the value, and these are the measured value, and then you take the ratio. So if it's perfectly on lambda CDM, everything will be on top of this black line. This black dashed line is a W0 WS CDM model, which is the best fit to DESI. And you can see there's a slight deviation from best fit, and not all the points are even on top of W0 WS CDM. So there are lots of, these are all small fluctuations given the error bar. And so based on this, now you can go ahead and do the last part of the analysis, which I showed you as a Fisher forecast yesterday, but this is the real data. You can measure W of Z, so equation of share as a function of redshift. If you just use DESI BE plus CMB, you get this 2.6 sigma deviation from lambda CDM. If you combine with different supernova samples, something like Pantheon, this is the luminosity distance part of the measurement, you get different constraint depending on what supernova sample you look at, 2.5, 3.5, 3.9. Right? So supernova sample is playing a lot of role here as well. And so this is very interesting. You can talk about, okay, what are the implications, and given lack of time, I guess I'll just rush through this, but I want to show this. So what is happening, and I think often, at least I didn't realize this so well before making this plot. If you have a matter-only universe, the scale factor evolves like this, okay? And the A double dot, the double derivative of scale factor evolves like this, where this is deceleration, this is acceleration, so negative versus positive, and this is look back time, and that's today. This will be future, this will be past. I'm showing you future because if I don't show you future, all of this will look like a very small effect. So it's important to note that all of these things we're talking about is a very small effect if you just think about today. Now, if I look at cosmological constant, so dark energy with the equation of state W of -1, you're going to see that they are more or less follow closely, and in fact, only in future it's going to deviate significantly in this scale. If you look at the derivative, then there is a constant shift, and it's only recently it has come to the acceleration phase, and now it's going to sort of go do a runaway effect. If you look at dark energy, which is -0.5 equation of state, which is the quintessence regime, then you're going to sort of transition into the acceleration regime, but you're going to stay very close. You're not going to have this runaway. Right? So in terms of the scale factor, it's a bigger difference compared to the A double dot. And if you look at the phantom regime, the big leap, you're going to go even faster than the cosmological constant. Here basically the energy density is increasing for the dark energy, so start dominating more and more very quickly, and so very soon things will run away. And well, very soon is very long time scale, so don't worry about it. Not in your lifetime, but very soon. And the best fit model for DESI, which is shown, is the red line, which is going through So in terms of scale factor, it's actually very close to the matter only, if you just don't pay attention to the details. But if you look at this double derivative, you see that it transitioned to accelerating universe earlier than the cosmological constant. But then given the kind of crossing we are observing, kind of the parameter space it's there in terms of the W0 WS space, it actually turns back. And then it goes to the, so we are again in the regime where it's almost acceleration of 0, and then it will go start decelerating again finally with no acceleration regime. So this is the best fit model, but it's only 2.5 sigma deviation from lambda CDM now. And so we are trying to see whether this holds up with bigger data sets. So now we have 3 times bigger data set. We're trying to see what happens when you reanalyze that. So I'll basically stop here with the end of this slide, but I think you already know what the whole procedure looks like. You start with BAO, you think about, okay, how to do the optimal survey, try to optimize that. From there, you'll have measurements of proper distances as a function of redshift, which can help you constrain physical parameter like A of t, like I showed in the previous slide, through model through equation of state W of z, and then this will then make you ponder about various different scenario what our true universe is dealing with. Yeah, so I'll stop here for today, and I'll take any question if you have. So more data, what we expect is that the error bar of the measurement is going to reduce. Whether it will be stronger deviation from lambda CDM or not, we'll only know after looking at it. What we can promise is the error bar of our measurement is going to be smaller, but whether it's a stronger deviation from lambda CDM or not is something only time will tell. No, it's just a CPL parameterization of W0 WA. So there's a specific value of W0 WA which is there in the paper, or I can tell you, I don't remember, but it's essential CPL model, yeah. So just linear. That's because when you make that statement that dark energy is going to dominate, you assume that W0 equals to -1. The equation of state is -1. But if you say that equation of state is not -1, then that picture will not hold anymore. And this is the new picture. If you take these values as this W of z I showed you, if you say this is the W of z rather than -1, then that will imply that, and that will automatically adjust the dark energy and matter domination error. Oops, sorry. Yeah, go ahead. Yeah, so typically when universe is accelerating, it's accelerating because dark energy is dominating. That's how you call the dark energy is dominating. Why is it turning down? So the reason it is turning down is because once it's there, it's dominating. The equation of state is such that the equation of state is deviates from -1 and becomes smaller and smaller. And so the energy density of dark energy start to reduce at some point. Once it start to reduce, it will again become subdominant, and so you'll not. In fact, you'll go back to the deceleration phase. It's basically for the purpose of data, we are basically saying that this kind of evolution is preferred. But of course, we don't have like now you need to ask, okay, where exactly this transition is happening? How to explain it from fundamental physics? You have to work out the model, and that is not done yet because we are not expecting dark energy equation of state to cross -1. So you have to consider all this scenario and see what will explain this. Yeah, so for something like, for example, crossing W equals to -1 will, if any single field model, if you're looking at, what's going to happen is that there's going to be some strong discontinuity. For example, sound speed can be infinity. So if you want to avoid that, then you need to say that, okay, dark energy is not just one field, there are multiple fields, more than one field, and then different field dominates in different areas, so there is some evolution, and that's why we are seeing a behavior like that. So to avoid this kind of discontinuity, if you want to do. Yeah, it's just a I think it's another coincidence in cosmology, which then we'll ask philosophically, why is that the case? Yeah, so people have done this analysis with even like free form dark energy, where you don't assume a parameterization, but say, let's say I'm trying to reconstruct with a Gaussian process, so it can take all different forms. And then they found more or less consistent result with bigger error bar. So the evolution crosses -1 in a similar fashion, but everything is wider. So your significance reduces. So it's not even 2.5 sigma in that case. So it could be like that flat is also not far from explaining that, right? So in terms of the chi-square difference, it is smaller once you look at a law of freedom like that. So the precision of measurement is going to depend on what kind of parameterization you're going to look at, right? So if you allow more freedom, what's going to happen is that generally your errors are going to become wider and you'll get less significant deviation. If you allow less freedom, on the other hand, which is also some people have done, you're going to find that it's more significant. But then you have more strict assumptions about the model. Thank you.